So I I don't think it was this class that asked me about question 2. Because I think a lot of you guys, I don't know if you made it to question 2 in class, but you were able to do the first 2 questions in the packet. However, I think it was 6 hour when we kind of discovered that question 2 was set up different. So I don't know if you guys got there or not, or if you just kind of left it not done. That's fine too. So this example right here kind of ties directly to example 2. It actually is the same type of question as the first one that you did yesterday in class, but it looks different, and so everybody kind of got thrown off by that, especially the way it's presented. So if I read this, it says, shown below is the graph of the derivative f of some function capital F. Assume capital F of -3 equals -8. What we had been working with, was capital F was the integral from some number to x of little f of t. These were all the problems we were doing. And so on this one, it says the same thing, but it presents it differently. It says that the graph is, what does it say? It says little f is the derivative of big F. So I could see from your viewpoint how that would not necessarily click. I'll explain the derivative portion here after this problem, because that kind of leads into our next topic somewhat. So if I see capital F of -3, that means that I was finding the area under the curve, starting at some number and ending at -3, and the answer was -8. So I don't know where it starts, but that technically doesn't matter. If my answer is -8, that means currently my area is at an answer of -8. So if I look at choice A, whatever it's called, problem A, capital F of 2. Well, 2 is over here. I still don't know where things start. I don't know where I'm supposed to start counting area from, but I know that right here, the answer was -8. So if it's now changing to 2, the new answer is going to be 36 added on to that answer. So remember how the accumulation function, it doesn't actually matter where you start. We can kind of just keep adding the area pieces as we move. And that's what we're going to use here. You don't need to know the beginning information. We know that we're going to be adding the 10 and the 26 onto the -8 that we started with. So what is that, 28? And then the very next question says f of 6. Well, I go look where 6 is. That's kind of at the end of this picture. And I'm going to take the previous answer, and then I'm going to add on these 2 shapes or these 2 areas that I can see. So I can see that I have an 8 that's below the axis, so -8. And since I'm moving to the right, I kind of follow normal positive, negative things. If I was moving to the left, then I would reverse positive and negative. So I have -8 plus 14, 34?
Wait, sorry, why did you subtract 8?
Because it was below the x-axis. So anything above, let me start that one over. As you move to the right, like what we consider normal direction, anything above is positive, anything below is negative. If, for whatever reason, you are moving to the left, they are reversed. So if you're moving to the left, above is negative, below is positive. So that's where this last one comes in. F of negative 5, well, that's right here. If I start from negative 3, what we were told at the very beginning, that was the negative 8, and I'm moving to the left, this won't be a positive value, it'll be a negative value. And this is almost exactly how question 2 is going to be set up in your homework. And when I looked at the problem, I guess I didn't even think of it, that it would be different for you guys. So you probably stopped at the end of 1.
I was able to get 4, I think.
Huh?
I was able to get 4.
Yeah, theoretically you could have done all of them. I figured you would just probably want to see today's information before you went on. And the good thing about them is there's only 4 questions. They're not necessarily horrible or slow. They're just... So this isn't a bad section for homework. Before I move on, I kind of want to explain derivatives and integrals for you guys, because I think that's probably the part that hasn't really been explained in the packet, even though you're supposed to just kind of like get it. So position, velocity, and acceleration to me are really good examples, because I think most of you guys get that the derivative of position is velocity, derivative of velocity is acceleration. Like, we did that a lot. So are you guys okay with that part? Okay. And every time we're doing derivatives, it represents like slopes and stuff. Okay. Integrals, what we're doing right now, they're often referred to as antiderivatives. Like, they have different kind of names. That means you're doing the exact opposite. If I integrate the acceleration, it's going to give me the velocity. If I integrate velocity, it's going to give me position. And that's what we've been doing here lately, even though I'm not really talking about it. So little f has kind of been what we've been working with a bunch. And we've been integrating little f. The answer to this, we've been labeling capital F. So in your mind, if you need to, kind of picture this. That, like, if you pretend this is velocity, then you know your answer should come out as position. Now, what you're running into, and you're going to get some questions on, is it's going to be talking about the derivative of capital F. The derivative of capital F would end up being
Little f?
just little f, correct. So it's going to be presented to you kind of like this, which absolutely can look confusing. Oops, what? So the derivative of the integral of f. If you, in your head, if you kind of get that derivatives and integrals are opposite things, they essentially cancel out. Now there's absolutely going to be details that we're going to learn. So it's not like that simple, but that's how it works. It's no different than trying to say squaring and square rooting. They're operations that we do something with, and if they're opposite ideas, they cancel each other out. So that's kind of what we're working with here, with integrals. Where to go? It says, since the area under f is positive on the interval -3 to -1, we know that the graph of f must be something. We can kind of think about this as that. Okay? So if this is the derivative, and it's saying your information is above the x-axis, do you remember back from last trimester? What did we figure out? If derivatives are positive,
Base function's increasing.
then that would mean it's increasing. It basically means the slopes are positive. So that's what this answer blank is kind of asking for. It's not asking for details. It wants you to kind of get what's happening. And honestly, the next 2 pages in our packet, that's what it's about. And if you can kind of keep straight what is considered derivative original, then it usually makes it easier. If you can't, then it becomes really difficult. Right here, it says, since the area under F accumulates at an increasing rate from -3 to -1. So we're kind of looking at this little white area, this little 10. Well, like if I kind of look at this, the areas are getting bigger as we move along. And so the derivative of this would be positive. And we would know that because it's got a positive slope. This is, oh, it doesn't, you're right, I'm sorry, back up. It doesn't even say what you're supposed to be looking at or looking for. It's asking you about concavity in part E. It's asking you if it's concave up or concave down, even though it doesn't say so. Like that, to me, is kind of difficult the way it was worded. It's going to be concave up because this is at an increasing rate, and this represents the derivative. So the derivative of f prime would be second derivative. That's concavity. Because this is going up, it's a positive concavity. These next 2 pages are basically dealing with trying to decide how the things relate to each other. And I've found it easiest over the years to try and not think of this as little f. I just think of this as capital F prime, because then I know it stands for a derivative, and I try to work with it like that. I don't really care about us drawing the graph of it. Do you want me to kind of go over this with you? Probably, okay. I certainly can. So right here, in the directions on number 6, it says that G is the integral of F. Okay? So G apparently is what we're going to be calling capital F instead on this problem. If that graph stands for F, I don't want to think of it as F. I want to think of it as G prime. But like if you're doing the AP test, there's nothing wrong with you writing little notes to yourself on the graphs and things like that, because you can write directly in the booklet on what's going to help you figure and keep things straight. So this is labeled F, but it's the same thing as G prime. So this one says F is positive on the interval 0 to 8. So G is what? And these stand for slopes. So this means these are positive slopes. So this would be increasing. F changes sign right here at 8. That's what it's referring to. By changing sign, it changes from positive to negative. So positive derivative, we just wrote down, stands for increasing, right? What do negative slopes stand for? Decreasing. Oh, you don't have colors on yours, do you? Does it like look different shaded or something?
Yeah.
Okay, so you can tell the difference between the two. What is something called when we change from increasing to decreasing?
Maximum.
Yeah, and if you need to, picture it in your head. Increasing to decreasing. That would be a relative max. These are the types of questions you're going to get in the homework, if I remember correct, on 3 and 4. That's why I thought it'd be good for me to kind of go over this, how it's set up. Okay, this says the graph of G is decreasing where F is what? And we kind of just wrote this on the picture, or I did. It's decreasing where F is below the x-axis. Go ahead, Casey. Yeah. Ask it out loud.
Oh, I just said, couldn't I just say negative?
Sure. Absolutely. There's going to be lots of ways you can answer lots of these. Graph is G is decreasing where F is below the axis for values of... I don't even know what's supposed to go in that spot.
Probably negative infinity to 0 and a to infinity.
Oh, like the x values?
Yeah.
I mean, we don't know that it goes past, but I'm assuming it does. Should we go to E? I feel like you could answer D on your own. The graph of G is concave down. Is it going to be too much if I call on somebody?
Oh,
I don't know how uncertain you are on this topic yet.
I think I could.
Okay, how would we figure out where G is concave down?
It's, okay, so it's G is concave down is where F is decreasing, right?
Okay, yep,
Because the derivative of F would be negative, which means negative concavity, which means concave down.
yep. So concavity is the second derivative. Our picture up here stands for the first derivative. And if you're looking at a picture, the way you determine derivatives is slopes. So wherever this picture has negative slopes is where G would be concave down. So G is the only thing we don't have a picture of. So the graph of G is concave down where F is decreasing. So on this particular picture, it would be from 4 to infinity. And then the last thing we're going to ask, this point on the very top, what is that going to be considered? So that stands for something. I mean, that's obviously the maximum right here, but because you can look at the picture and that's the top.
Is it the point of inflection?
Yeah. So if we're talking about slopes, this right here has a slope of 0. That means its derivative, which is G double prime, is equal to 0. So possible inflection points were when the second derivative was equal to 0 or undefined. This is equal to 0 right there. Because the slope of this picture is 0, that means the second derivative is 0. And it's concave down after, concave up before, so it alternates concavity. Now, in my opinion, This is much harder to fill out because it doesn't give you any kind of direction. You just kind of have to like know this stuff. Where usually the questions you'll be asked, like say on the multiple choice parts of the AP test, is they would have a picture there, and then it would specifically say, where is the inflection point? Or, where is a critical number or a critical point? And so in your mind, you would be able to think, how do I find a critical number or an inflection point? And you can figure that out from the graph. So to me, that's a little bit easier because you have something specific you're looking for, where this is kind of just general, where, we're just saying, what does this stand for? And it could stand for a couple things. And so that's harder for your mind to kind of focus on a topic. But if nothing, I wanted to fill this out so that you guys had some guidance to know what to look for. You guys are giving zero indication today of how this is going. This is not bad to good. Where are we at? Oh, like I should have gone way faster.
Yeah.
Oh, why didn't you guys say so? What? Oh, all right. Everybody's just kind of staring at the screen, and that's not normal. Down here, it does directly tell you what things stand for, so I don't know if you probably saw that while we were doing the problem. And that's fine, that's what it's for. Like, use this as guidance if you need it to try to remember things. But that's why I wanted to talk about what stands for derivative, original. You kind of have to know the layout with derivatives and integrals. Okay, that's it. So you guys theoretically have enough information to do all the homework. What do we have? We have almost a half hour left, which is kind of shocking.
We ended 104? Is it 104 that we end? Or when do we end?
No idea. 104. Yep, 104.